And today we'll hear from Cole and Robby about reconstructions of oils. So, go ahead.
Right, hopefully I set everything up correctly over here. So I'm Kelson-Packer, that's Robby Kramer over there, and today we'll be talking about reconstructions and oils. Quantum theory here. So once again, having issues. Okay, so I'd like to start by talking about so-called principles. Now, kind of nice example of this is Einstein's special relativity, which people like to say is beautifully derivable from just two main ideas. First being that the laws of physics should be invariant under, simple or export Poincaré transformations, and that the speed of light should be constant in all reference frames. Now, this is all very nice in special relativity, but when we turn our eyes to something like quantum mechanics, axioms tend to be a bit less elegant, shall we say, and have this sort of problem here that we postulate that there exists this thing called Hilbert space, except that we actually care about projected Hilbert space. Have these states that are permission, non-negative trace. We have these expectation values. We have this weird idea that states evolve under this central extension of it. It's just a big. Then have measurements, and that's even further solidity. This, I just took these from that book over here, but most textbooks really aren't much better here. Now, Egon might have to complain about this, but Egon can complain about a lot of this here. Now, the reason why this is the case is that a lot of textbooks produce these axioms to be things that are used. They're useful things, and you can make nice homework problems out of them. So we have easy answers a lot of the time. If you're using a better textbook, like say Kelson-Packer, you'll usually perceive like some kind of rough analogy. You say that you have these things that are called states, which encode some description of your system. Say that you have some way of doing time evolution, whether by Hamilton's equations or through the Schrödinger equation, which is this has a nice geometry. These both have nice geometry. There's both ones here. You have this idea of getting expectation values through certain kinds of averages. All right. Now this is all very good. These classical analogies we use, they need to explain why we need to change our mathematics when we look at quantum mechanics. They don't really give a good sense like what's the actual physical intuition behind us making all of these changes in the first place. Now, the point of reconstructions and foils is to attempt to better understand these principles that are going into quantum mechanics. Reconstructions try to rederive quantum mechanics, so using maybe more natural axioms, and the idea is to try to gain insight by comparing all these different equivalent formulations of quantum mechanics. Meanwhile, foils have typos, and it's trying to describe what quantum mechanics is not. The idea being that what can and can't emerge from the theory is in some sense a foil to quantum mechanics. Tells you what's unique and special about the quantum mechanics that we use. Now, the entire one of the reasons you might like to think this is interesting is that if we can get better axiomatizations, get a better idea of what the core of what quantum mechanics really is. You might say, like, okay, maybe you can have better ideas like what advantages quantum mechanics has in that case. Maybe that's a very ambitious way of saying this, but it's one argument you can use if you're writing grades, I guess, for definitions. Now the question is, what kind of axioms do we care about? Maybe we don't actually really care about this axiom, so maybe we're just kind of forced to care about them because, it's what other theories do or what other context tells us we care about them. We have to care about, we have to have some kind of probability of quantum mechanics in some way. We have to match experiments because it turns out we usually don't know what measurement comes from getting advance. We like to talk about some notion of causality. This is going to be weaker than strict determinism. We like to have some way of making some kind of logical predictions about this given information we have. Now, locality here, this just comes from, there's a nice, yes.
Just to make sure, causality up to the probability, basically.
What?
Like, causality, weaker determinism means you can just say this is the probability distribution if that's.
Well, so it'll depend on the authors, my understanding. So if you're looking at, your nice general relativity textbooks, they have their specific definitions of what things like locality mean. From what I've seen with papers I've been looking at, maybe just an artifact of their age, they'll use slightly different definitions. I'll go a bit more into some more concrete definitions. Here. Okay, the locality, we have to at least consider locality because, a lot of successful theories do tend to be local. Finally, we have this idea of completeness, which is just saying, well, we can use our theory to describe whatever we actually care about, at least maybe not perfect. But something physical has some counterpart in theory that can study. But as we all know, when we talk about, conventional quantum mechanics, we know that there's tensions between these things here. It's not so straightforward, for certain more concrete definitions of these things, for them to actually all hold within quantum mechanics. And now, so just a kind of example of maybe a little of a foil model, I guess, if we strictly. I'd like to remind us all of this Specking's toy model that we covered last week. Now I say we, but I wasn't actually here. Last week, my person vacation during that time here. But now, just as a quick reminder, so now the key idea of Specking's toy model is knowledge balance. Amount of knowledge you have about the ontic state of the system, which kind of reflects what's really going on in a sense, is equal to the information being lacked in it. Now here I'm using this picture nice balance scale here. Now we know this cat on the left is adorable. However, on the right here, we don't know, and in fact we can never know so long as we think the cat is cute. We can never know who's dragging kitty litter into the human shower a few rooms over from the litter box. And we can never know who is in that human shower singing during the middle of the night. We can never know those things, at least so long as we know that the cat is cute. Now, Specking's toy model here, we know, or at least we should have learned, that reproduces several elements of quantum mechanics. You have teleportation, quantum teleportation. We have no flow. However, notably, Specking's toy model does not reproduce these ideas of non-locality and textuality appear in quantum mechanics. Now, for my part of the talk, I'd like to focus on non-locality as a theme because it's one very common recurring element in reconstructions and portals. Now, to kind of start this off, I'd like to talk about a little bit of a lecture, I'm not quite sure what, by Einstein's Solvay conference in 1927. Now, the setting for this is this idea. You have some particle impinging on some screen. It's a little hole in it. Past that hole, you have some kind of magical hemispherical detector that has unit efficiency on all sorts of nice things going on, right? Now, the single particle diffracts, and you can ask, okay, probability of the particle being detected, A or B, should be equal. Roughly would say it's given by this kind of expression. And it should be non-zero, this detection event. Now, let's first ask a fairly dumb question. Are these the probabilities that A particle is detected at A or B? If we're just talking about sending one particle in, or the probability that the B particle is detected at A or B. And now let's ask a third question. What's the probability that the particle is detected if this one particle is detected at both A and B? Well, we can say, well, basic probability should factor like this with this conditional probability here. But if we're assuming some kind of locality, Einstein would argue, well, this conditional probability shouldn't actually depend on what's happening at B here. So it should just be the same as probability at A here. When you do that, you start to run into a problem here because we know the probability of A and B are not zero. So it should follow the probability of detecting this one particle of both A and B should also be non-zero. This tends to contradict experience. We're not detecting two particles, we're sending one particle. Yes?
Yeah, I don't really understand or follow the argument that so A shouldn't know about B, but there's only one particle, so shouldn't it be the probability of A given that the one thing is that B is zero?
Well, again, if it's local, because this would be detected at the same time. the detector at A shouldn't know what's happening. So it should not depend condition on whether or not the B has thing.
So I guess the idea is that if there's a element of reality associated with A, element of reality associated with B, having to do with the part being detected or not, then whatever there is there shouldn't have.
I'm not sure the element of reality would depend on the language on science using at the time, but if that's language, my point, yes, go ahead.
And then A and B sort of events sort of happen in a space like way.
Yes, there is space like separate, there's no message between these two detection events. And now so the reason why I'm bringing this up, and the reason why I'm deciding this 5 minutes, is that this is kind of a silly. It's ignoring questions of how the measurement devices actually work, it's ignoring conservation laws that we should be caring about. Is this really how we should be understanding locality in the first place? We can ask, well, we're thinking about particles here, what we're talking about passing a basket, would it still make sense here? But the key point why I'm raising this is that it brings at least 2 flavors to combine here, because really, the reason why Einstein seemed to have been raising this first is to talk about interpretations of quantum mechanics, how to understand the wave function here. It's also about non-locality. So these are 2 flavors that can be fruitfully combined in consideration of foils and reconstructions, and that's why I brought this talk here. Now, what I'd like to direct to is this paper in particular by Kerrigan and Stevens. And now the primary idea is to say that non-locality of quantum mechanics is easier to establish for so-called theories of quantum mechanics, and the definition of that I'll get into in a little bit. But first, I'll have some definitions which may have seen last time, may not, and I was there, so I don't know. We have this thing called ontological model for theory. The idea of an ontological model is you posit some kind of context space which contains so-called context states. Context states here being some collection of something that specifies the complete properties of the system. Some conventional quantum mechanics orthodox interpretation. You'd say your context space is your Hilbert space, and your context states are your various wave functions within these words here. And now further requirements on these models. They produce certain probabilities, say probability they produce some object state, given you have some preparation you've got here. Probability that you detect some measurement outcome K, given that you have some object state, and given that you're doing some measuring of M. You also have this requirement of consistent marginalization, where if you average over the object state lambda here, then you will reproduce this probability of getting measurement outcome K, given that you're doing measurement method M and you've done preparation B, which is all to say that if you consider preparation here as producing some normal quantum state. This last thing here is just saying that, okay, regardless of how we're parameterizing our true state of the system, our true notion of the system with this context space, we at least have to reproduce standard quantum probabilities. Okay. And now this paper considers 3 different kinds of models, so-called psi-complete, psi-supplemental, and psi-epistemic models for quantum mechanics here. The idea that in a psi-complete theory, the wave function psi fully and uniquely describes reality. The idea of psi-supplemental theories, that psi is a real thing, it does describe some reality, but you can have some additional things there. These are like certain kinds of hidden variable theories. And we have these so-called psi-epistemic theories, where the wave function is just some kind of heuristic. You have multiple different psis describing the same reality. They all describe to a different extent, maybe different levels of usefulness, and there's different ways of thinking about this here. Now I'd like to quickly go over 3 examples. Now, the details of these examples, they do not matter, do not get caught up in the math. What's important is just how these are examples of these 3 different kinds of theories here. First, for psi-complete theories, is Beltrametti-Bugajski model. I'm almost certainly butchering both, so I apologize here. But now, as the paper, this Reconstructions paper posits it, this theory is really just recasting the standard quantum mechanics in this ontological model language here. Because you say, well, your ontic space is just your projected space. Your wave function again is everything. Your theory is complete here. And now, because it is essentially just quantum mechanics, again, recast in slightly different language, well, then of course it's just going to reproduce the quantum mechanical probabilities. You just stress things up in a place. Get a direction go to quantum mechanics. Figure here, okay. So this figure is just a way of describing what this ontic model and this measurement method is. So your ontic space capital lambda, as I said, this is just your wave function space, your Hilbert space or projected Hilbert space to be pedantic here. And now, as I mentioned before, one thing you have to specify are these various probabilities. What's the probability of having some ontic state given that you have this wave function psi? Well, in this case, where our ontic space is just Hilbert space, this is just a delta function, like so here. And you have this other constraint of trying to figure out, okay, what's the probability of getting measurement outcome k, given that you have ontic state lambda and you're given some measurement speed m. Well, this will also just be the same as regular quantum mechanics. You have this trace of the state with some effect e here, like so. Now, as for the picture, this is just a way of depicting the ontic space. The ontic space is capital lambda here. You say that, okay, for a spin half particle, you can parameterize the pure states by the surface of the Bloch sphere. Say that, okay, you have a wave function psi, which is specifying the actual state here. Probability of having some specific ontic state given that wave function is the delta function, hence its shape is this big sharp peak here. You have a question of what's the probability of detecting some state B given that you prepare the ontic state lambda, which again is just psi. But that probability of doing that measurement is again just given by this thing here, this trace of whatnot, and this will be related to a cosine function, essentially cosine of the angle between these vectors. Now, again, I'd like to specify that there are all these details for these models, but these models themselves aren't very important here. But it's important in this discussion, it's just how there are the examples of these different kinds of theories, these psi-complete, psi-supplemental, psi-epistemic theories. For the psi-supplemental theories, there's this apparently famous Bell-Merman model, where your object space is a product of two Bloch spheres. The first Bloch sphere being essentially just enacting like the previous model, where your distribution is just given by the delta function here. But then you have this second Bloch sphere, which has a uniform probability on it. And so you see the sense in which this is a supplemental theory. You have your regular Bloch sphere that was being seen before for these spin-out particles, but then it's being supplemented by this extra Bloch sphere, which is encoding some kind of hidden variables, if you would have it that way. And now, so the way the measurement works with respect to these hidden variables here, I say the probability of getting some measurement outcome B, given that you have Bloch vectors lambda prime and lambda double prime on the two spheres, is given by this heavy side step function. And what this is all saying is that, okay, if B, the thing you're measuring, is pointing the same direction as the sum of these two vectors, this should be a lambda prime here and lambda double prime, then you'll have probability 1 getting that specific measure outcome B, as opposed to measuring along the opposite direction here. And now it can again be shown that measurement probabilities still reproduce standard quantum mechanics. And now for the third example, you have this Cauchy spectrum model for the psi-epistemic theory. The ontic space in this model is actually again, yes,
I just want to clarify on the previous one, does that mean, does that mean we have essentially a hidden variable model for a single qubit? Is that what they're showing, or is it a different thing?
it is hidden variable model for a single spin over here. You have you can think of, okay, we have our regular spin half particle, which is living on the sphere. And then we have this extra hidden degree of freedom here, which is determining the measuring outcome if you measure along some axis pointing in direction B. Go ahead.
But this isn't like the classic hidden variable theories of like Bell's.
I don't believe so, like apparently this is a classic well-known version, but I don't think it's the version. As I understand, this specific recasting is due to Merman, who was taking something Bell was doing. Which was maybe more like this. Go ahead.
So to understand this model, am I to think of the first sphere as kind of like a classical spin?
No, it's in the regular quantum. You have your regular quantum, your regular wave functions, like for spin half particles. But it's being supplemented by these extra degrees of freedom on the second sphere.
For what purpose?
To determine the measurement outcome here. So you normally think like, okay, we have a random measurement outcome. Normally we just think about that one sphere. But it here is that the details of the distribution on the second sphere are actually controlled what that measurement outcome is. And the way they control, as I said before, is via this probability here, where you say, okay, I'm measuring along an axis pointing in direction B here. I will, with probability 1, get the, let's say, spin up along that direction. If the state along lambda prime and the summing that with the state along lambda double prime is pointing in the same directions.
Okay,
So that is, so the addition of that second variable here determines what before appeared to be a random measurement.
okay, so but it's not a. If I'm not using the Born rule in the first sphere, how is it the same quantum spin?
What I mean by this same quantum similarity is that it's just being described as described as having vector on the.
Okay, yes, but that could also describe that the spin classes.
If you want to think that way, but the entire point of this presentation is that you have your classical wave function being augmented by this hidden aspect. You had a point?
I'm a little bit confused. Is the measurement deterministic here? In the
It
sense
would be
that.
deterministic if you knew what
Oh,
the
if you
second
knew that,
variable is. The entire
okay.
point is that it's hidden.
Yeah, okay,
You
okay.
don't.
That's the point, right?
Yeah.
Yes. Now, now again, I'd like to repeat here that the details of these models aren't what's important. What's important here is that they're examples of these three theories. Okay, and now the third example is the so-called stem. Again, here, the object space is just the block sphere. But now it has this non-sharp probability distribution here, with probability of having some object state given their size given by this function here. We have this size function which is saying like, okay, if lambda is pointing in the same direction as b, that'll be 1 if it's pointing in the opposite direction, that'll be 0. And it's augmented by this angle here, which is given by this double bracket, and then, normalized by this 111, right? Now, if you want to turn this around, ask, okay, what's the probability of getting measurement outcome v along an axis given this object state? It's also given by a similar kind of 0, 1 heavy side separation here. Now, the entire point here is that different kinds of b's, different kinds of lambdas are satisfied for multiple b's, so long as you choose some b. So if you say lambda is pointing in this direction here in this hemisphere, any phi, any wave function pointing in that hemisphere is according to this inequally good description. It still works out here. But point is that combining that still with this probability of an object state given the side, it could still reproduce normal quantum mechanical measurement outcomes. But again, the bottom line here is that in this case, the wave function is at the static. It's just, what's the knowledge you have or what do you think the wave function should be? We could have multiple different wave functions in this model, still describing the same object state, still the same fundamental reality. Now I really need to speed things up here, but again, all three of these theories are reconstructions of spin 1/2 quantum mechanics. If you go through all the math, which I don't have time to do, then you get the same probabilities. They're not really doing anything new in that sense here. Now, furthermore, they're all connected, which you might expect because they're producing quantum mechanics. You connect them all just by taking appropriate marginalizations over hidden variables, essentially here. So if you marginalize over variables in one way, you can move from this supplemental theory to regular spin 1/2 quantum mechanics. If you marginalize over slightly different variables, turns out you can move from this supplemental theory to the psi-epistemic theory here. What's interesting though, is that objective indeterminism in one of the theories is just a matter of epistemics in the other theory. Now, the final takeaway being from all this is that you can essentially interchange certain axioms. Like you might say, okay, you might change indeterminism as an axiom theory, but you can get rid of it and replace it with a certain amount of epistemics. So it's not a definitive axiom here. So again, this is just one example of this kind of reconstruction structure, where you can take your different axioms, you can still reproduce the same quantum mechanics at the end of the day here. But now, the thing I introduced this originally was a connection with non-locality, and there's a specific takeaway that comes from thinking about what are specifically called ontic theories. Now, the idea of an ontic theory is that this is a case where the wave function is, in a sense, a real thing. It's either, in a psi-complete theory, it is the entire reality, or in a psi-supplemental theory, it describes part of it. It has to be supplemented by other details described before. But the wave function is still, in these so-called ontic theories, a real thing in some sense here. Now, if you want a concrete description here, the idea that theory is ontic essentially means that, okay, you take the product of these probabilities, you have some ontic state lambda, given that you're doing some preparation producing wave function psi and v, and this should be 0. What this is telling you is that the wave function, if you're given the wave function, this corresponds to a distinct Bohr class of distinct ontic states, meaning that if you take different wave functions, these will produce, even if they're only part of a description of reality, they'll produce different ontic states here. Now, so we're talking about locality earlier, and I guess might as well just throw everything on the slide at once here, since I need to be going faster here. Now, for this purposes of this paper, they say that a model is local if it is separable and locally causal. Separable here, meaning that if you take a system R and you split up into some subsystems, the ontic space can be described as a Cartesian product of those subsystems. Locally causal is maybe a more complex definition, which I don't have the time to get into. But essentially, it just means a causal, that you have causality in a nice, suitable local sense here, where the probability of, an event at B, given that you have some event at A and some event at C, the ontic state at C, and the ontic state at C contains everything you need to know about A, then you can just ignore A. You just deal with that ontic state at C instead. And now the only complaint I would have here is that these words mean completely different things if you actually know differential geometry in general. But that's the complaint that doesn't matter for the purposes. This is just me explaining the picture.
What's J minus?
So this is part of the description that I don't have time to get into, but J minus refers to the causal past of region A. But again, let's not get into these details here. Okay, point here. So the authors essentially modified an argument of Einstein from 1935, which is not the EPR paper published the same year, to show that taking these definitions and locality is at odds with the assumption you have this ontic theory, where the wave function is, in some sense, a real thing. The idea here is this: let Alice and Bob share, some kind of nice spell state like this. It is known that Alice, by choosing different measurement directions, say along the z-axis or the x-axis, can steer the kinds of states Bob will get, whether Bob will similarly get z states or x-axis states here. Now, so again, I don't have time, I need to really hurry up things, so I'll just say that the key result when you go through all this through with this typo here So you have this case where this product of probabilities, this product of having ontic state lambda, given that Alice is measuring states plus or minus, or times the probability that you get ontic state lambda, given that Alice is measuring 0, 1. This must be non-zero, or at least some choice of plus minus or 0, 1 here. Idea here is that this contradicts the assumption that the theory was ontic in the first place, because that was the definition of an ontic theory found here. Now, again, unfortunately, I have very poor time management, so I cannot go through this, but it's not too here. Now, so we've seen that certain axioms are to a certain extent interchangeable. We've also seen another thing is that ontic models are necessarily non-local. Now, a question you can ask is, okay, we had this case of looking at locality as a potential axiom before. What if we took the opposite? What if we said, okay, let's have non-locality as an axiom in the first place? Now, let's say that we still have causality. The theory is both causal and non-local. It kind of has to be indeterministic by definition here. Because multiple different things corresponding in non-causal regions can all affect what's happening at your one point here. And so that's what this paper is about, which is exactly what it says on the tin, as it were. And now, so we can think of two different ways of defining non-locality. They can, for this paper, briefly mentions like, okay, we can talk about non-local equations of motion. It's really more popular to talk about kind of Bell functions, non-local correlations as a way of considering non-locality here. And now, so I believe this seminar covered CHSH last week. I again wasn't there, so I don't know. Again, the idea is you take two systems, take one system with two pieces that are far away, and pairs of observables A prime, B prime, which all take values plus or minus 1. Consider the correlation between them, which can be given by this expression. And if you assume locality, then after some manipulations, you can show we have this kind of constraint on this particular sum of correlation functions for measurement apparati A prime, B prime here. However, we know that standard quantum mechanics in fact permits a value of 2 square root of 2 for this, which violates that bound, showing non-locality. This should be 1 before. The thing to note is that if all the correlations here were independent, 2 roots 2 wouldn't be the upper bound would actually be 4 instead. You can show this by just playing some games here. So you ask, okay, what does causality actually imply for correlation functions? Or how do these authors take causality to say what about probabilities and correlation functions? The idea for them about causality is that you have 2 parts of the system, Alice and Bob are distant apart. The choice of measurement basis by Alice, say, should not affect the probabilities that Bob observes. So if, say, Alice is doing measurement, so I guess I'm using Bob here, so if Bob is using B prime here, method B prime, or is using B, probability of Alice getting measurement outcome plus or minus 1 is equal in both cases, and both may be attained as this marginalization over the outcomes that Bob will get, regardless of which measurement method is used here. Now, if you just kind of arbitrarily assign measurement probability distributions, this is one convoluted example here of such a distribution that will work. All these probabilities being 1/2, all probabilities not listed being 0. Then it can be shown, which I cannot show because I'm lacking the time and space on the whiteboard. Yes.
How are the middle 7 terms there, how are they different from each other? P of A, B, -1, -1, and then that number 6 times.
Oh, that's called me.
That's called cut and paste.
Yeah, that's called me cut and paste and down paste.
How should I make those?
What should
Well, I can quickly bring up here, but again, the mathematical details.
1, -1, -1, 1, -1, -1.
Yeah.
Okay,
There are certain problems. So I apologize for here. Okay. But my big point here is that there is some way with this constraint on marginalization of assigning probabilities such that this Bell sum here, this Bell sum of correlations has a value of 4, which is greater than the 2 root 2 predicted by regular quantum mechanics here. So in other words, you can posit like, okay, there might be some kinds of theories that can produce, in a sense, stronger correlations than quantum mechanics. As an example that hopefully I've actually done everything correctly on this for, consider a rotation invariant so-called super quantum state of spin half particles. Now, the fact that the state is rotationally invariant means that correlations should not depend really on the direction of any individual axis, but only the angle between the measurement axis of the 2 particles you're considering. So consider rotating, your axis, both your axes by pi. You can convince yourself the probability of both spins being up should be the same as both spins being down. Probability of one being up and one being down, the same as probability to swap the order here. Justification being this, like, okay, if you consider these solid arrows to be the up direction, these dashed arrows to be the down direction. Well, probability of up in this direction, you just change your reference frame. Should be the same as the correlation for up in these directions instead, which is down of the original directions. And the same argument applies for this case up here as well. Then you have this other idea that if you consider the angle pi minus theta instead, this just corresponds to flipping one of the measurement axes. And now what this paper is, it says, okay, take this kind of convoluted super quantum correlation function, whose effects are described on this bottom left figure here, which paper admits is convoluted, contrived here. Okay, but then consider measurement axes A prime, B, A, and B prime, which are separated by angles of pi 12ths, all on the same plane here. Well, A and B are pi 12ths apart. A prime and B are pi 12ths apart. A and B are. That should not be A and B, that should be A and B prime, I believe. Is pi 12ths apart. But A prime and B prime, this is pi 4ths apart here. So you compare and you look at this correlation function over here, okay. Pi 12ths has a value of 1. Pi 4ths has a value of -1. So this sum produces a 4 here. It's another super quantum violation here. And again, this example is rather silly, but it shows that correlation stronger than quantum mechanics can be managed with certain principles here. Okay. So what's the takeaway from this paper? Well, this paper kind of said, let's assume non-locality and relativistic causality. Can we get something like regular quantum mechanics probabilities out of it? And its answer is, well, no, because we get stronger correlations if we just assume these 2 axioms with the definitions they support that. So they find like, okay, with this foil theory, you actually need more constraints to recover standard quantum mechanics. Yes?
Yeah, just curious, what can you do with these super quantum theories, like computation?
I believe this has been studied, but I do not know the answer.
I
You know, if,
So I can say one thing is that, memory serves, if you remember the famous MIT starting was equals RE. The complexity result, if you replace the correlation with stronger correlations between the different, what do you call it? Provers, then you don't get as much, like, you actually go lower. Oh, like the set of quantum correlations is very complicated. For PR boxes is actually simple to describe.
Interesting. Thanks.
as I recall, things I've heard before is. I might be misspeaking here, I might be shots back nonsense, because there are all people saying like there's physical arguments to some like why you shouldn't have some of these quantum correlations in reality. Maybe that's part of people say like, okay, if you assume these super quantum correlations exist in reality, in various complexity hierarchies collapse, so you don't expect them to collapse. This is how I've heard it explained before. Again, I don't know any of these details, so I'm probably wasting people's time. Things. you know, that's one thing that, you know, people like to say, it's like, or at least fact data, it's like, okay. Do super, you know, there's this such as this idea of quantum advantage, what super quantum phenomena possess further. Which is, this was a thing people were considering for a time, maybe people on this. I do not know anybody who this. Okay, I wasted a lot of time at this point, so let's ask to Rob. Let's change to Robby's PowerPoint here. I can share the screen then, because even though I'm in the same program, it can. It's come up with here, it's complaining about, oh boy. Now, we'll just arrows.
I do not have much time, this will mention a fair bit. We didn't time manage this super well, but anyway, so Paul gave you a sort of broad idea of how.
Your last question, so
That's-
you can go like at least 10 minutes over. but-
All right. Yeah, so Cole gave sort of a broad idea about spoils and reconstructions. I'm gonna go through a couple, just 3 examples of how foils are. I guess these are 2 foils and one sort of generalized reconstruction schema. That these sort of give us some idea of why we need the strange axioms of quantum mechanics that we're currently dealing with. And then the third one, does anyone here like GPTs? Like, do they study them intensely? It's like you're gonna want to throw a rock at me by the time I get through it. I mean, you could probably squeeze a good semester, 2 semesters content out of GPTs, but I'll try and give you a brief introduction to see what we're thinking about. All right. So first up, we have real vector space quantum theory. When I was looking at Cole's slides, I was like, oh my gosh, Cole has so many jokes. I don't have good jokes. So this is on the title slides for each of these, I've written down chapter 11 of The Hitchhiker's Guide to the Galaxy, where they invent the impossible or infinitesimal improbability drive, which I would read to you, but I'm just gonna wait till I see some like chuckles or thumbs up in the room and then move on, because I think it's faster to read it than. So real vector space quantum theory, you might think, okay, you know, complex quantum theory, like it's just, maybe we're just containing another, you know, rather than having n variables, we have 2 n variables when we try and represent things with the n variables when we try to represent. Couldn't we just use that many scalar vectors to, you know, have the algebra and scheme that makes that still generates the same physics we see with like our quantum mechanical predictions. So here I have, this is, by the way, I'm gonna bridge a lot of the mathematics here because it's a lot of mathematics. Down here I have archive links of the papers that I'm talking about that you can go and read for the proofs and, you know, fine-grained details. They're all published, but I give you the archive links because I believe in free and open access to information. So yeah, so here's Woodard's 4 axioms. Basically, the only things he's going to change in jumping to the real vector space quantum theory is he's going to replace the Hilbert space, space over the real numbers. I don't know if it's still a Hilbert space.
It is.
It is? Okay. And then he's going to replace the unitary operators that generate our like time evolution or whatever with orthogonal operators. And the first thing you might think is like, wait, how are we going to actually time evolve these systems? Because, you know, the Schrodinger equation from regular old quantum mechanics has this eye sitting there. It's going to, you know, rotate your system around in a complex space. Turns out you can sort of cheat it a little bit, but replacing your IH with a anti-symmetric matrix S, which Wooders is using S as a credit to Stupelberg, who I believe is one of the first people to have really thought about real vector quantum theory. And then your state's just going to evolve according to E to the ST. You know, sort of, we've all solved this differential equation before, I hope. Yeah. And then the problem with real vector quantum theory, which he goes real vector space quantum theory, which Wooders goes through in some terribly long line of mathematics, reasoning about mutual information, is that you essentially have optimal information transfer in real vector space quantum theory. So, unlike our standard quantum mechanics, yeah, I've got that. So let's say Alice prepares some state, applies some unitary over and sends it to Bob, when Bob knows what psi is initially, but he wants to figure out what unitary Al's apply. Turns out that even if you're using the SIC POVM, which is like the greatest general measurement you can use. Once your Hilbert space is dimensionality 3 or greater, that's not actually covering the full probability space. You don't maximize your mutual information as fast as you possibly could be something. But in the real vector quantum theory, Bob always has some universally optimal measurement. Which is all I have to say about that, because the math was kind of over my head. All right, next we're going to move on to modal quantum theory. After you guys finish. Thank you, Isaac. All right, so yeah, modal quantum theory. This is a paper by Schumacher and Westmoreland. I don't think Schumacher invented modal quantum theory, but when I read Mobit, I was like, Schumacher has done it again. But so basically, modal quantum theory is interesting. It's like instead of our actual quantum physics, modal quantum theory is a possibilistic theory. It's not interested in the specific probabilities we get from quantum predictions. It's just interested in does something happen, is an outcome possible or impossible. So the simplest example you can write, your state's going to exist on some vector space V on the field, on some given field. Simplest vector we have is this, the simplest field we can write down is the field over the integers modulo 2, where we have these 3 unit vectors, just 0, 1, and then some sigma is 0 plus 1. You have these inner products. Now, I was reading this on a plane, and I was looking at like this one, and I was like, shouldn't that not be 0? But then I forgot about modulo 2. So you do the inner product, you get 2. 2 modulo 2 is 0. It also gives the space a nice symmetry.
Let's see.
Oh, that's right. Your dual. I have these dual vectors defined as like A, B, C. So for you have your vector space V, you have the dual vector space V that generates these outcomes. So like essentially, A would just be 0 dagger, B would be 1 dagger, and C would be sigma dagger. Although that doesn't really work because these are all a real vector space. And also, it's a binary thing, right? You can just have 0 or 1. These things can just be possible or impossible. Evan, what's up?
Yeah, I think maybe you just explained it now. What do you mean by possibilistic, like possibilistic?
Like you're not differentiating the specific probabilities of some measurement outcome. You're just asking, is it possible for me to do this
0, 1.
to get this outcome or impossible?
Okay.
So the 0 would indicate impossible, right? The
One doesn't mean certain, it's possible.
It means possible, right?
So really it means not 0.
Yes.
Yeah, it's a binary sort of description. Oh, sorry.
So one of these is C. How do I interpret outcome C?
The interpretation is the funny business. I think you probably would need to map this to some physical state and then understand what that physical state is talking about. Which the paper, as far as I was able to tell, did not actually do any of that. I'm not want to give a better answer than that.
And if you look at the outcomes, right, the table outcome C means it's either 0 or 1, but it wasn't sigma.
If anything,
Yeah.
if anything, it might be 0 minus 1 or correspond to that as a raw vector. Like, well, if we think of sigma as kind of a
sure.
plus vector,
Right,
and C might be a
Yeah,
minus state.
I hear that, yeah.
So the dual space. So it looks like you have 3 unit, unit, I guess, doesn't.
They're not, I guess the last.
Yeah, they're vector.
Vectors, yeah.
But it's 2-dimensional space. Because you have 0, 1 and then a
Well,
combination.
the field is over Z2, but I think the space ends up being 3-dimensional.
But it's 0 plus 1 equals 0, equals sigma. So.
Right, they're not quite linearly independent in the sense.
Right, so their dimension is not gonna be 3.
I think, right, in modal theory, I think you lose like the idea of like orthogonality as such.
Well, it's not orthogonality, it's just linear dependence.
Right, okay. Sorry, what was your question?
My question is, that seems to be a 2-dimensional space, and then the dual space has 3 vectors, so. I'm kind of confused. But we don't have to dwell on this.
Sure, I mean, I just Like you can see that they're, depending on what you write down, you get different outcomes. So that naturally, like if I didn't have, well, I guess. Yeah, I hear what you're saying.
Okay, well, we're chat up offline.
Yeah, I think it is supposed to be three-dimensional, just because like,
I mean, I promise
Because
you,
you-
like this is what
yeah.
they said.
you're over just this field, so that sigma is not like. It's not like it, I think it's like a formal superposition, so it's like not actually in the span of these two, I think.
Okay,
I don't know,
alright,
maybe I'm wrong.
I guess you can think of sigma as representing like I have a mixture of both 0 and 1. Because right in the modal case, it's like if you have this mixture and I do some measurement, well, I could measure it in 0 or I could measure it in 1 because I have this mixture. Because both measurement outcomes are now possible.
I'm not, no, I'm not disputing that you have three vectors, I'm just saying that dimension of the space. Is 2, so you have 4 vectors in total. The vector
Oh, yeah,
0,
right,
the
cool.
vector 1, the vector 0 plus 1, and then the actual 0
Sure.
vector.
Okay,
That's all I was gonna say.
I got you. Did I have a question over here? Okay, thanks.
I think,
I guess you did say.
I don't know, maybe I
do.
don't understand the question Mohammed is asking, but it makes sense that 0 means you will definitely see 0, 1 mean and not never 1. And 1 means you will definitely see 1 and never 0. A sigma means you could see both,
Oh, yeah.
which is fine, so.
Yeah, it's just,
I mean,
the problem
I-
I have is the dual space has 3 unit vectors, I'm kind of confused by it. I guess it has 3 unit
I
vectors, but it has 4 too.
I whipped this presentation up and not nearly enough time to do it well and look it over, so that's more on me in the preparation.
I took it, sir.
Yeah.
Let's move on.
So, okay, something funny that you maybe wouldn't expect to come out of this theory that still exists is we can see entanglement. So they write the singlet state S equals 0, 1 minus 1, 0. Then you can take this, hit it with some effect E, that could just be like A, B, or C, or some combination of therein, because, you know, just do the math works out at 0. It's impossible that you'll have correlated measurement outcomes if you measure hit each of these individual moments with the same measurement. What is measurement exactly? Well, again, it's just assigning, you know, your whatever modal subspace into, you know, possible or impossible. So I can do some measurement and it's possible if for some effect in E, that we have some non-zero, you know, inner product is quite correct, but that operation there gives some non-zero for some effect, and otherwise it's impossible. And then what's interesting is, you know, when we do measurements in standard quantum mechanics, we have a normalization condition. You can actually recover a similar normalization condition because you expect to not be able to. If you have some complete, like if you do some measurement over a quantum state, you expect to get something. You don't expect to map quantum your modal state to, you know, annihilate it completely. So
Right, so,
Yeah.
so here, it looks like it's possible if the one inner product is non-zero. But
Correct.
what if I have 2 and they kind of cancel out?
well, that would be 0 then.
That would be impossible.
Right, yeah.
Okay.
Okay. How did I misspell possible? Alright, sorry.
Possible.
Alright, and we can talk about modal evolution. Now, we don't carry over time, and a continuous evolution, but, in standard quantum mechanics, most of us know, right? I don't know, all of us know, you can write some quantum channel is just, you know, tracing out the environment of the initial state, answered with some ancillary environment state. And that actually has a Krauss decomposition in terms of sum over these Krauss operators, AK. And you can actually do a similar thing in modal quantum physics, where you have a remapping onto these Krauss operators. Oh, by the way, these angle brackets I'm using, at least in the modal section, mean the linear span, right? Because if I get a measurement outcome. Trying to think of a good intuition. Basically, like the linear combinations always are going to apply here because we're not interested in the magnitudes of these inner products. We're interested in the like just the binary 0 or 1, this stuff. Yeah, and then so here's what these modal Krauss operators look like. which has a very similar flavor to the cross operators and standard quantum mechanics. Then we also have the cross operator normalization condition, right? You know, in standard quantum mechanics, I guess it would be AK dagger, sum over AK dagger A should be the identity. This is what we get here. So it's the same idea. We shouldn't be able to map a non-zero state to a zero state gives this. All right, possibility. So, possibility tables, they're gonna tell us, they're gonna give us a full idea of these measurements and tell us what's possible and impossible. Where these X's are gonna, so on the rows I have, like the grand rows, I have X, Y, or Z is like the three possible single mobit measurements. On the first qubit, and the rows correspond to measurements on the second qubit. That's the binary outcome of 0 or 1. Or binary outcome of like positive or negative along these axes. Then this is what you get for the single state earlier, singlet state that I mentioned earlier. Oh yeah. So we have a no signaling principle, which tells us that we shouldn't be able to have the measurements correlate. Measurement outcome on one qubit shouldn't correlate to the measurement outcome on the other mobit shouldn't correlate. So essentially what that means is you're doing kind of a Sudoku thing where if you have an X in one row, it better, or an X somewhere, it better have a corresponding X, you know, above it vertically or below it. Vertically or horizontally. So like this X implies that there needs to be one of these two X's in this one. And also this X and this X, or the other two. What's interesting is there's no signaling, kind of like Paul mentioned, we can still write down a PR box, this would be the modal PR box. You would replace the X's with a 1/2 back in probability.
So there is such a thing as modal entanglement?
Yes, but this isn't like a real fit. Okay, none of this. This isn't a physical modal state, or this isn't a modal state that you can actually write down because it's through a proof covered in this paper that we really don't have time to get into. But sort of like the same reason. It's akin to the idea that you can't write down a modal state, or you can't write down a PR box, under traditional quantum mechanics. PR box state, traditional quantum mechanics. So I guess here's a quick summary. So despite losing all the things on the left, we can still, modal quantum theory still allows us to recover all the things on the right, which is, quite remarkable. I don't know what this says about like the grand nature of reality or anything, but I do think some of it's interesting, and especially this. You get your non-classical computation back, just I think about what's possible and impossible. I have no idea how that works, but don't ask. We're just doing a lot of reading today. You guys just looking at the slides.
We could say, okay, for example, these lower quantum theories, they do not have convexity here. For example, just take it over there. So we need, if we want to have regular quantum mechanics, we need to investigate convexity. So we can ask, okay, what if we assume something like convexity as an axiom instead? And this will lead into these generalized probability theories of discussion, right?
Yeah. All right, so now we're going to get into generalized probability theories after. That's the new probability generator. I honestly was like reading the first actually like this. I was reading the first GPT paper that's in the first reference for this topic that John put together. And I was like, man, I really am these physicists. I can't stay the smart ass. There's so much math going, anyway. It turns out you don't need that much abstract like algebra, like a line laser. Maybe you do. So, all right, how does one generalize probability? So, essentially, GPT is like a convex operational approach to quantum mechanics. So we have as an axiom that your states form some convex set, and that they're operational, and that we have measurements and outcomes based on those measurements and the state being measured. And the only, like, the biggest difference, the big relaxation, like classical probability theory of these GPTs is that we relax, the ability to perform simultaneous measurements. You might be like, there's other relaxations. I'm sure there are. This was what, Howard Barnum told me. And Alexander Wilson. Oh, and then here we have this quote from Barnum. The resulting post-classical probability theory, while in some respects rather conservative, presents a vast, poorly explored, and rather wild landscape within which even quantum probability theory seems rather tame. It's kind of like, oh, this is the Wild West out here, GPT land. So whatever Cole was saying about getting a, whatever will get you grant money, it seems like the masses would have a lot of fun with it. Yeah.
So PR boxes are like a part of these.
Right. Yeah, the idea is like quantum mechanics is just one, small point on this ginormous convex cone. Or I guess slice of this convex cone. And what's interesting, so the idea, what Barnum says is like we're standing outside of quantum mechanics to better see what it is we're standing in. So here's one way you might articulate the beginnings of a GPT. So you have the state space is a set of points, it's convex, it's closed, and it's closed and bounded. And then it's a subset of a real finite dimensional vector space with Euclidean topology. That last one just sort of makes it easier to articulate convex and bounded, or convex and closed. Yeah, so it's a lot of math. Basically, we're just some quick definitions, which we all understand because we're quant theorists on mechanics. X is a state space, if it's pure, if any mixture you can write down that actually gives you X, so long as you're mixing two elements within the state space, just implies that they're the same element. So you can't mix two different elements and get X, that means X is a pure state. And then the converse, it's mixed if that's not true, if there's some non-equal two states that you can mix and get X. And we can prove as a theorem that like the extension of if you write X K that of pure states, then the convolution over that extension is K itself. There's a lot of theorems in this paper. I'm only giving you like 3. K is a state space, the effect out. K is a state space. All right. So you have state spaces, and then you have the effect algebra. So like, what can we actually do on these states? Essentially, we have functions that act on the states in our state space that give us a value between 0 and 1, or is inclusive. That is linear, so it's linear with respect to the mixing of the states. Right? Then we also have an important, like, I guess, unity function you could call it, which is just for every state in the space that what you do will give you 1. Whatever operation you do gives you 1. Applying 1 sub K to any element in K gives you, in the state space gives you 1. And then AK, I am getting right with the mathematical details. There's not really a better way to, sorry. Right, okay, then the proposition is that we can define AK as like the vector space that affine functions on K, then AK dagger is some cone of positive affine functions on K. So when people talk about like a probability cone, AK dagger is what they're talking about. And then you can prove that AK is the span of the effect algebra, and the effect positive affine cone is the cone of the effect space, the effect algebra space. Anyway. All right, okay, so now we have some examples that might ground this a little bit better, make it less abstract. So classical theory is just pretty straightforwardly some list of probabilities, so some n-dimensional probabilities. N-dimensional classical theory is just some like list of probabilities and sum to 1. And you can pretty easily convince some people can pretty easily convince themselves that that means that the space itself, the state space itself is simplex. And then the effect algebra we can write as just a bunch of delta functions essentially. And then what we can show is thinking that through, what you get is that the unity function is just the sum of all these individual delta functions. And then I get to show you pictures. Wow, we've been missing this. So for n equals 2, your simplex is this blue line, the state space is the blue line up here. you're somewhere between zero, the S0 and S1. And then the cone is this. So you can see. These, I don't know why these letters are so different. This is B0, so it projects S0 to 1. This is S1, or this is B1 over here, that's the same, goes out right, just like S1 goes out to the right. So it has, you know, the DIJ property. And it's perpendicular to S0. Here's the origin, sorry. And then you can see that the unity function is just the sum of those two. You can kind of see that, right? Like we can play the same game for higher and higher orders. I guess these are the codes we talk about. I assume there's some relation between this with the A of S3 star dagger and A of S3 dagger, but it's a bit lost on me. Oh, and then for n equals 3, your probability simplex is like a triangle. It's a two-dimensional shape. And then for n equals 4, I can't show you the cone, but I can show the effect algebra, but I can show you the simplex itself. It's like a four-dimensional thing. And when I say on the W equals 1 plane, I mean the fourth coordinate is 1 in this four-dimensional space. One sort of novel implementation. There's also quantum theory here, obviously. We wouldn't learn a lot because we already know quantum theory. Well, yeah. You can recover the same like tensor problems, right? So you can imagine like these boxes, the box world theory is just these, you know, some boxes that take inputs and give outputs. There's this input output table for like the simplest one. You send in a bit, you get out a bit. There's the four boxes that can exist in this world. So we don't have full linear or affine independence, but what we do have is, so you can see that like summing 0 and 1. These two boxes will give you the same output as if you summed the 1, 0, and 0, 1. So it makes like 50% chance of getting out 1 or 0 no matter what you put in. And that gives you this three-dimensional space. Three-dimensional state space here. Has this two-dimensional. Right? Oh yeah, three-dimensional state space. And then the functions you apply here are just like inputting functions into the boxes. So it gives you these over here. So here's putting 1 into the box, or here's inputting 1, here's inputting 0. And then there's a lot of math in this paper that you might want to go look at. I don't know. Yeah, all right. And here's one last quote that I will read forward. He said, "There's an infinite number of pseudo quantum theories outside who want to talk to us about this script for adjacent realities they've worked out. It's after they get the improbability driver." All right. Yeah, I guess any last questions? Thanks for listening.
So GPTs are sort of a more general way of constructing theories of probabilities in a convex way, I guess.
Sure, I guess for now, I mean, maybe some crazy math that'll come out with something else. I can't see where the generality, like how you get more general.
Pretty damn.
I mean, sorry, this is by sigma algebra, this kit has this associated measure, but it doesn't have like all this nice linear algebra structure you get from sigma. Okay.
John was a great help with this whole show. Oh, and yeah, I think this informational foundations and boys book is actually really good if you guys want to start sinking your teeth into what these theories look like. Cole, instead of covering real vector quantum theory, Cole wanted me to cover quaternions because I'm like, it's like real is boring, and I think I agree with
Well,
Cole.
no, my comment was they should have, real is more familiar because it's reals. Quaternions are fancy, like fancy.
Oh, I see.
It's all about fanciness.
And then did you actually do some stuff with octonians too?
So octonians are
Like,
not
but-
associated, quaternions are not units. Octonians are not.
Okay, this is not.
But was all talking
Yes, the talk is done, we're not recording.
It's all off script now.
Oh, next time.
Understood it.